My name is Ulrich Rührmair, and I'm going to discuss our paper Virtual Proofs of Reality and their Physical Implementation with you. This is joint work with Leo Martinez Hurtado, Shaolin Shu, Christian Kreh, Christian Hilgers, Dima Kononchuk, Jonathan Finlay, and Wayne Burleson. Here's a short outline of my talk. I'll start by giving you the basic idea and the basic setting of this new cryptographic and security primitive that we call a virtual proof. And I will then deal in sequence with three example virtual proofs of distance, virtual proofs of temperature, and virtual proofs of destruction. And my talk concludes by a summary in section 5. Now, what are these virtual proofs all about? Actually, I got some problems with this here. Okay. So we have two parties interacting with each other. Alice acting as the prover, sitting in a local system S1, and Bob acting as the verifier, sitting in a local system S2, and both are connected via digital communication line to each other. And now Alice makes a physical claim concerning her system S1 or concerning certain objects that are present in her system S1, and Bob would like to verify that claim by communication over the digital channel. Just in order to familiarize you a little bit further with the type of claims that I had in mind when I was designing the primitive, here's a list of example claims. Alice could claim, for example, the temperature, the humidity, or the pressure in her system, the relative location of two objects in her system, the destruction of a certain object in her system within a certain time period. That's an interesting one, isn't it? The authenticity of video or audio data recorded in her system, or the configuration or state of a certain hardware in her system. Is it untampered or not? And as you can see from that list of example claims, we're going beyond the classical secure sensor setting regarding the type of claims that we're trying to prove, but we're also going beyond the classical secure sensor setting in a second aspect, and that second aspect is that we prohibit the use of classical secret keys within Alice's system, right? So no classical secret keys shall be used within Alice's system. And just to get that straight, because I think it's a very important aspect of our work, where does the novelty of our new concept lie in? And the novelty is, first of all, that Alice tries to prove a general physical claim over digital communication channels, and secondly, that she tries to do so without using classical secret keys or classical tamper-proof environments or classical trusted sensors in her system. Now, it's a natural question to ask, why did we choose that setting, right? And there are two reasons for that. First of all, there's obviously, at least in my opinion, some aesthetic appeal in that. It's a natural extension of classical, mathematical, crypto, and security into the physical domain. In particular, it's a physical version of interactive proof systems, right? And there's a second reason, which is no less important. As you all know, classical keys usually represent primary attack points. So the question is, why not avoid them in the first place wherever possible? And there's this striking quote by Ron Rivest from his keynote talk at Crypto 2011, where he said, calling a bit string a secret key does not make it so, but rather identifies it as an interesting target for the adversary. And if this is the case, and of course it is, then why not avoid such secret keys in the first place? That's the motivation. But having summarized the motivation, the next question, of course, is it possible at all to show something meaningful and something non-trivial in that quite restrictive scenario? Is it possible at all? And this is what the rest of my talk is concerned with, and also what our paper is concerned with. And the first example virtual proof I'd like to discuss with you is a virtual proof of distance. And as you can tell by the name, virtual proof of distance, it's about proving the distance of two objects, O1 and O2, in Alice's system to Bob. That's the idea in a virtual proof of distance. Now, it takes some thinking before you can come up with two objects that are actually qualified to lead such a virtual proof of distance. And the key idea that we had was to use so-called optical puffs. And the idea is that you use two small plastic platelets, each of dimensions 1 centimeter by 1 centimeter by a couple of millimeters in the Z direction. And in each of these small plastic platelets, there's a random distribution of light scattering elements. These light scattering elements could be small air bubbles or small glass spheres of micrometer size, anything that changes the local refractive index of these two platelets. And when you now shine a laser beam at these two platelets, the laser light is scattered multiple times and it interferes with itself and creates a pattern of dark and bright spots, so-called interference pattern or speckle pattern that can be recorded conveniently by a CCD camera. And the important aspect for our purposes is that this interference pattern critically depends on the unique structure of these two objects, on the distance between the two objects, and on the laser parameters P and alpha. P denotes the position where the laser beam hits the first object, and alpha denotes the angle by which the laser beam hits the first object, okay? And having made that observation, let me now tell you how this virtual proof of distance actually works. So first of all, I need to tell you that we discretized the distance levels, obviously, because it was no use to prove a full and continuous spectrum of distances, so we had to discretize the distance levels. And now we also assume that there's a private setup phase, and in this private setup phase, Bob does the following. For each of these discretized distance levels, he puts the two objects at that distance, d. He then chooses n random positions and angles and directs the laser beam at these n random positions and angles at the first objects. And then he measures and stores the n resulting interference patterns, okay? And having done all that, he creates and stores a private list that corresponds to that particular distance di, and then private list consists of n entries, and in each entry would have the position of the laser beam, the angle of incidence of the laser beam, and the resulting interference pattern. Okay, that's the idea. Now, at some point, so what Bob essentially does is he creates a fingerprint of the behavior of these two objects when they are placed at a certain distance di to each other. And he stores that fingerprint in his system. Now, at some point, the setup phase is going to close. Bob is going to remove his measurement setup from the two objects, and the two objects will be transferred to Alice. And now it's part of our adversarial model that some time passes, so Alice can prepare a potential attack, Alice can try to inspect these two objects. But then the actual VP starts. And in that VP, in that virtual proof, Alice puts the two objects at a certain distance dm. She claims that distance over the digital communication line to Bob. And then Bob remembers that he has this fingerprint stored in his system from this setup phase, right? And from that fingerprint, he looks up that particular list that corresponds to that particular claimed distance dm, right? It consists of n entries, that list. And from those n entries, he chooses R at random and sends over the points of incidence and angles of incidence of the laser beam of these randomly chosen R entries to Alice. And now Alice applies the laser beam for those points of incidence and for those angles of incidence to the two systems. She gets R interference patterns in response, and she sends over these R interference patterns back to Bob. And now you can guess probably what the decision rule is. Bob says, if the pre-recorded values from my list match the values that Alice sent to me, I'm going to accept the VP. I'm going to say thumbs up. I believe that the two objects are at that distance. Okay, that's the virtual proof of distance. So let me have a very quick and dirty security discussion due to time reasons. I think first of all it's interesting to ask, what does Alice actually prove to Bob? And you can see that she proves that first of all the two unambiguously identified objects, O1 and O2, are at a certain distance level at a certain point in time, right? Namely between the second and the third message of the virtual proof. So we can pinpoint not only the distance but also the two objects that were being used and the time at which the objects had that distance. Second feature that I'd like to discuss with you, it's interesting that in this particular protocol, not necessarily in all virtual proofs of distance, but in this particular protocol, all standard features of a strong PUF are actually required. So you actually do need the physical unclonability, the very large number of possible challenges, and the fact that the interference patterns cannot be numerically predicted or simulated. This is just for those of you who are active in the PUF community. You don't get things cheaper here than by using a strong PUF. For further security discussion and also for a description of a full proof of concept in hardware, please do have a look at the paper because it's all there. Now let's move on. Virtual proofs of temperature. The idea in a virtual proof of temperature is that Alice claims to Bob that a certain object in her system is at a certain temperature level at the time of execution of the virtual proof. Okay. There's, of course, a classical approach to that, using a sensor environment, trusted sensor environment with a secret key that is known to Bob. But of course, in this particular setting that I've described to you, in these virtual proofs, we don't want any classical keys. So this classical approach is not applicable, and we have to think about new solutions. And the key observation in that context for us was that one can use temperature-sensitive electrical strong puffs. So again, it's a certain puff type that can be used in the virtual proof. So we're using an integrated circuit / puff whose complex output intentionally depends on the ambient temperature T. And as you all know, this is exactly counterintuitive to what you would usually want to have in circuit design, right? In circuit design, you would like to design a circuit that is independent of any temperature variations. But in that the virtual proof of temperature, we intentionally like to use a circuit whose output depends on the ambient temperature level. And cutting things short simply for time reasons, you end up with a similar protocol as in the virtual proofs of distance. So you assume that there's a certain setup phase in which Bob collects a fingerprint of the input-output behavior of that integrated circuit. And this output then proves the temperature when Bob asks random challenges to Alice. That's the idea. There are three interesting aspects to which I'd like to point your attention. First of all, this establishes key-free temperature sensors. It establishes a form of temperature sensors that is free of any classical keys. And I think that's an interesting practical outcome that sort of drops out from our new theoretical concept. Maybe others are going to follow. But if you thought that this was all theoretical and too esoteric, here's a nuts and bolts outcome. We can construct temperature sensors that are free of any classical keys. Second interesting aspect, we led a full proof of concept on FPGAs via so-called XO bistable ring puffs. And this is a strong puff variant that is known in the puff community, or perhaps even I could say that is notorious in the puff community, for being rather temperature unstable. But in that case, we're turning this known weakness of the bistable ring puff into an advantage. We're turning it into something good. We're really turning lemons into lemonade here. And again, just as a side remark, again, all standard features of strong puffs are required in that particular protocol. Not necessarily in any virtual proof of temperature, there might be others, but in that particular protocol, all standard features of a strong puff are required. Again, for the complete protocol and for a full proof of concept, please have a look at the paper. Right, so let me come to the last virtual proof that I'm going to discuss with you, so-called virtual proofs of destruction. And this is perhaps the most mysterious but also the most interesting variant of virtual proofs that I want to discuss in that talk. Edis claims here that a certain unambiguously identified object has been destroyed or irreversibly modified in the course of the virtual proof. And when you think about it, that's quite difficult and counterintuitive, right? So assume that Alice would hold a piece of glass and that the glass would be smashed and scattered. How would you prove that the fragments originally belonged to that glass? Or perhaps a more striking example, if Alice would hold a wooden object or a tree, and if she would burn that tree and reduce it to a pile of ashes, how would you prove that this pile of ashes once was that tree, right? It's very difficult and counterintuitive, I think. And there's also no classical approach that I would know of that ever has addressed that question before. And nevertheless, we were able to come up with two implementation strategies for virtual proofs of destruction. They're both in the paper. The first strategy is a protocol that uses an optical puff inside a puff. So if you look at that figure, there's an inner puff structure and an outer puff structure. So the outer puff really physically encapsulates the inner puff. This is just an intersection, so you have to imagine that in 3 dimensions. And if you now want to collect a speckle pattern coming from that inner puff, you first have to remove the outer puff and thus to destroy the outer puff. And that's how we prove actually that this outer puff was destroyed. And there's a second implementation strategy. It's a quantum protocol. Our intuition here is that in quantum theory, measurement of an unknown superposition state amounts to destruction of that state. And we exploit that in a quantum-based virtual proof of destruction. The protocol, again, is in the paper. And for time reasons, again, I'm sorry that I have to refer to the paper. Complete protocols for both of these optical and quantum virtual proof of destructions, and actually a full implementation, a full optical proof of concept for this puff inside puff strategy can be found in the paper. Right, so let's wrap things up. What I've told you about in that talk is virtual proofs of reality. They are a novel cryptographic and security primitive. Their basic idea is to prove physical statements over digital communication lines without using classical keys and without using classical trusted hardware in the prover system. I gave you 3 example VPs, virtual proofs of distance, of temperature, and of destruction. And I'm also proud to announce that there are full proofs of concept in hardware for all of these 3 types of virtual proofs in the paper. So here's an image of that virtual proof of temperature where we used a dedicated oven and an FPGA, etc. And here's an image of that object which we used in our virtual proof of destruction. When you look at that object very closely, you might be able to spot that there are 2 different kinds of materials being used, an inner material and an outer material. And this is, of course, the inner puff and the outer puff encapsulating it. So there's a real full proof of concept in the paper. Now, what's the long-term vision? What is our long-term idea? The idea is that we want to convert physical objects or processes into binary data in such a way that you can later on prove that the data is authentic. And what do I mean by authentic? Authentic in my sense means that the data corresponds to a really existing physical object or a really existing physical process. That's the idea. So we're really trying to bridge the gap between the digital world or the virtual world and the physical world. Because as you all know, it's rather simple to doctor things and to doctor data in the digital world. It's not so simple to doctor things in the physical world. And we're trying to bridge that gap between the 2 worlds by our virtual proofs. That's the long-term vision, that's the long-term idea. And I think it's really fair to say that there are plenty of future research opportunities, both theoretical and practical. And I'd like to invite you as the community to join us in exploring these opportunities in the future. It could be a very thrilling and beneficial endeavor. But for now, thank you. Thank you very much.
Thanks, Uli, for the very interesting talk. Is there any questions? No questions? So,
There's someone over there.
yes.
Hi, Kevin Butler. I have a question about your, you had mentioned with the distance related protocol that you could make you could essentially prove that the optical puff was placed at that particular distance at a particular time. I was wondering why the adversary couldn't pre-compute all of the distances. I didn't see any notion of freshness in the protocol, so yeah. What prevents replay?
So thanks for asking that question. At some points of the talk, I simply had to cut things short, to fit into that 16-minute slot, so I'm very grateful that you asked that question. The thing is that the puff has very many possible challenge values, right? Too many, actually, to measure all of them, so you can't have an exhaustive list of all challenge response pairs of the puff in advance, neither by measurement nor by computation. That's one of the standard assumptions in the puff area. It originates from the original paper by Papou et al. In 2002 in the Science magazine. So it's nothing that we invented or nothing that we came up with, but that's one of the standard assumptions, that you can't simulate the output patterns and that you can't exhaustively measure all the possible input-output patterns. But that's a good question, so thank you for that question.
Hi, I'm Jonas Wagner from EPFL. I just wondered whether it would be possible to, for example, use a set of lenses or a binocular or so between the 2 objects to sort of simulate the distance that's much larger or somehow tamper with the laser beams in between the 2 objects or so.
Yeah, so that's a very good question, of course, but I think the problem is here that the light, so this wavefront, this light wavefront, when it leaves the first object is a very complex thing, so it has got certain relative phases, and if you would somehow use lenses, these lenses might actually change the beam and also might change these phases. So I must frankly admit that we didn't, of course, put that in our setup, so we never experimented with lenses, but I'm pretty sure that this would not work out because the phases would not be right. But thanks for the question, yeah.